In this video, I'm going to go through Theorem 11. If three parallel lines make segments of equal length on a transversal, then they will also make segments of equal length on any other transversal. Okay, when it comes to proving something in geometry, we usually have to use kind of previously found axioms and theorems to kind of build our case. So I want to mention kind of two that will be useful to us today. Okay, so the first one is to do with parallelograms. Okay, so I wanted to remind you that opposite sides are congruent. So what that means is opposite sides are equal in length. So AB is the same length as DC, and AD is the same length as BC. Okay, so that's useful for us to, first of all. And then the other thing that's useful is what is meant by congruency and congruent triangles. So if two triangles are congruent, that means they have the exact same shape and the exact same size. So all angles are equal measure and all sides are equal measure. And there's four ways to show that triangles are congruent. So side, angle, side. So if you can show that two sides and the angle in between are the same. Angle, side, angle. So if you've got two angles and a side. If you've got side, side, side. So if you have three sides that are the same, and then right angle, hypotenuse, side. So if you can show that you have a right angle, that you have the same length hypotenuse and one other side the same length, then you have congruent triangles. So I could work out that two triangles are congruent because of side, angle, side, for example. So if I've shown that it's congruent using side, angle, side, then it follows that even though I don't know what the third side is, that they must be equal as well. Okay, so let's have a look at the proof. Okay, so we're going to go through the proof now. So everything on this by the time you're finished will be what you need to have taken down and kind of learn. And for every proof that we do, so proof for Theorem 11, Theorem 12 and Theorem 13, you will have this kind of general layout to your proof that you need to know. Okay, so the first thing we need to do is actually state the theorem formally. So if three parallel lines make segments of equal length on a transversal, then they will also make segments of equal length on any other transversal. Okay, so this is what we're kind of basing our proof off. So we have this diagram where we have parallel lines L, M, and N, and we have transversals T and K. So what do we have? Three parallel lines L, M, and N intersecting the transversal T at the points A, C, and E, such that AC is equal to CE. So the line segment from A to C is equal in length to the line segment from C to E. Okay, and another transversal K intersects the lines L, M, and N at B, D, and F. Okay, so that's what we've got to start with. So what is it that we're aiming to prove? So it almost feels like we're repeating ourselves here because we have already stated the theorem, and that's really what we're trying to prove. But when it says to prove, I mean, what is the thing in reference to what we've been given that we need to show? And what we really need to show is that BD is equal to DF. So that's what we're aiming to do. Okay, construction. So a lot of the time, a construction is something that you draw that can benefit your proof. It just makes it easier to prove, and it's absolutely okay to put something else in. So through D, so through that point D, okay, draw a line parallel to T, okay, and it's going to intersect at X on L and N at Y. So it's going to go through line L at X and through line N at Y. Okay, so proof. The first thing I'm going to use is the idea of parallelograms. Okay, so ACDX. So I'm just going to highlight that so you can see it. So ACDX, that parallelogram, that's a parallelogram because AC is opposite XD and so on. And then you have another parallelogram there. Okay, so what we've got are two parallelograms. So AC is equal to XD. Why? Because they are opposite sides on a parallelogram, and likewise CE equals DY. Okay. Now we know that AC is equal to CE because we were given that, and XD then must be equal to dy. So if you think about it, sorry, I changed my pen. So you don't have to take this down, I'm just trying to explain. AC is equal to CE, but AC is also equal to dy, or sorry, XD. Sorry. So that means that CE and XD must be equal. But likewise, CE was equal to dy, so XY must be equal to XD. So if something is equal to two things, then those two things must be equal, that kind of idea. So we can actually use that to show that XD is equal to dy. Okay, so we're now going to look at congruent triangles. Okay, so in the triangles BDX, so I'll highlight that in blue, so that triangle there, and triangles YDF, which I'll highlight in green. XD equals dy, okay, and we've shown that in the previous part of the proof. And angle BDX equals angle YDF. Okay, so we're talking about that angle there is vertically opposite that angle there. Okay, so we have a side and we have an angle BDX equals YDF, and then we have another one, DBX. Angle DBX is equal to angle DFY. So DBX, okay, so that angle there is equal to angle DFY. And why is that? Well, they're alternate angles. You know your Z angles. Okay, so we have parallel lines, we have a transversal, we have got alternating angles. So we've got side, angle, angle. So angle, side, angle is, we've used that to prove that the triangles are congruent. So if the triangles are congruent, that means that we've got three equal sides, which means that side BD must be equal to the side DF, and that's what we were trying to prove in the first place. And because we've proven our point, we write down QED, which basically, I don't know what it is in Latin, I've tried to pronounce before, but it basically translates to, which is what we were asked to show. So it's kind of saying, look, we're done. Okay, so there's our proof. Take it down, try your best to understand it and learn it off. This video is always going to be here, so you'll always have a chance to look back over it if you need an explanation.